This is Uark, Physics and Human Affairs, Lecture 16, The Energy Challenge for April 21st, 2020. Please take notes on this lecture. And we begin now, as we usually do, with poetry. Say it with me. When small nuclei like hydrogen combine, we call it fusion. When large nuclei like uranium fly apart, we call it fission. When I say physics, you say rocks. Physics! Did you say it? Yeah, you did. Energy is what humans need to thrive. It's the currency of the universe and of our economy. Remember, energy is formally defined as the capacity to do work, though I would add it's also the capacity to heat things up. Energy can be used to do either of those things or both at the same time. So humans use energy in a variety of ways. In fact, anytime you do anything, you're using energy, even if all you're doing is thinking. That is using energy. It's converting chemical energy in your body to electrical energy in the synapses in your brain, and a good chunk of that is dissipated off as thermal energy. So the human body uses calories, which you eat from food. If you ride a bicycle, that also uses your calories. If you drive a car, most likely, unless it's an electric car, you're going to use gasoline, which is chemical energy. The appliances in your house use electricity, which probably, though not definitely, will come from natural gas or coal. It could also come from wind or nuclear or solar. Manufacturing uses all sorts of energy. As humans have, throughout history, humans have used more and more energy. So this graph shows the daily energy use per human being throughout time. So in prehistoric times, humans just used the food that they ate. Once they learned to tame animals and burn things, why the amount of energy they used, include not only from their bodies but from by using other animals and burning things, increased by a factor of 5 or so. The Industrial Revolution is when we learned to build machines, and so that increased energy consumption even more. And once petroleum was found and we learned to use petroleum, which is cheap and plentiful, or it was and is for now, then energy consumption per human being skyrocketed. Here in the United States, we have been using more and more energy since about from 1950 to about 2000, and energy consumption has leveled off since then. Since 2005, coal has been decreasing. There's just not that much of it anymore. It's harder and harder to mine. Natural gas has been increasing, mostly because of fracking, which has a lot of environmental impact on its own. Renewables have been slowly increasing, but the overall use of electricity in the United States has leveled off since about 2000, and we'll talk about why that is. As of 2019, 38% of all the electricity generated in the United States is from natural gas. That number has increased significantly over the past couple of years. Coal has decreased as quickly as natural gas has increased. Nuclear power remains steady. Renewables are slowly increasing. Renewable sources of energy are ones that you don't use up. Wind. Wind keeps blowing. Hydro, that means using waterfalls to turn turbines to generate electricity. Solar power, the sun keeps shining. Biomass, this is burning living things like crops or sometimes garbage. And geothermal, that is using heat from the earth. Now, renewables generally are better for the environment, not always, but generally. And the renewable energy source that has increased rapidly over the past 20 years or so is wind. Wind, you may have driven along the highway and seen wind turbines, just these these beautiful turbines spinning and spinning. They're generating electricity. And they have the great advantage that you can double use the land. So farmers can put wind turbines in their fields and still use the fields to graze animals, for example. Solar power is increasing slowly as solar panels become cheaper. So before, what we saw was electricity generation. It did not include, say, transportation, but this does. This graph is total energy use in the United States. We're talking power plants, natural gas piped into your home, and transportation also. So once you include transportation, petroleum, oil, gasoline, becomes the dominant source of energy. Fossil fuels. This is the dominant source of energy consumed today. This is the burning of ancient life, usually things like algae. They don't come from dinosaurs. They come from plankton and algae, that sort of thing. So this includes oil, coal, natural gas, and it's the majority of how we get our energy. 81% of U.S. energy consumption is fossil fuels of some sort, and they have some great advantages. They're cheap, they're plentiful, there's a whole industry of them already in place. The infrastructure is already in place. We have gas stations everywhere. We have oil refineries, pipelines, oil cars on railroads, and oil tankers all over the place. But fossil fuels are killing us. Burning fossil fuels pollutes the air and leads to climate change. Pipelines that carry oil, they break. They're just pieces of engineering, and under enough strain, eventually they're going to break, and they do a lot. Oil tankers, they crash and spill ridiculous amounts of oil. And burning fossil fuels, as with burning anything, releases carbon dioxide into the air, which contributes to climate change. This image that you're looking at here is from Mayflower, Arkansas in 2013, when ExxonMobil's Pegasus pipeline broke and leaked 300,000 gallons of fossil fuels, of diluted bitumen, all over town. 22 homes were evacuated. This is an aerial view of the Keystone XL pipeline that leaked in November 2017. There were a whole lot of protests to prevent the Keystone XL from ever being built, and the courts went back and forth on it. Eventually, it was, and it broke. So let's play a game, Toxic Trivia. Write down the answer in your notebook if you think you know it. Write down your guess or the answer if you know it. How often on average does a fossil fuel pipe leak, burst, or explode in the United States? Is it A, every 2 weeks, B, every 2 months, or C, every 2 years? Let's think about it. All right, let's eliminate something. Not every 2 months. What's left? Yeah, every 2 weeks in the United States on average, which means, if that's true, there should have already been a bunch of them by now in 2020. Unfortunately, I couldn't find the data for 2020, but I found the data for 2019. Just in the first 3 months of 2019, there were 7 pipeline bursts, including a natural gas and oil explosion and fire, a natural gas pipeline exploding, 31,500 gallons of crude oil spilt, a natural gas fire, another 1,800 gallons of oil spilled, another natural gas pipeline exploding, oil and natural gas pipelines exploding again, and another oil spill, 12,600 gallons. This was all within a span of 2 months. Some of the biggest oil spills are on the ocean. There's a huge dead zone in the Gulf of Mexico from this, and also from pollution coming down the Mississippi River. 2010, the Deepwater Horizon drilling rig from British Petroleum, now known just as BP, I think, exploded in the Gulf of Mexico. 11 people died. Oil spewed into the Gulf for 5 months, leaking hundreds of millions of gallons of oil. 5 million pounds of oil were cleaned off the Louisiana beaches alone. And carbon dioxide is the regulator of Earth's temperature. And we've pumped more carbon dioxide into the atmosphere than the Earth has seen since very early in its formation, since very early in geologic history. And a lot of the carbon dioxide that we're pumping into the air, most of it comes from burning fossil fuels. And go back to Chapter 9 and Lecture 9 for more details on that. But fossil fuels are not the only way to get energy. We also have fission reactors, nuclear reactors. This has some advantages. There's lots and lots and lots of energy available in the nucleus of the atom. So nuclear fission reactors have lots of energy. And although a nuclear reactor is very expensive to build, once it's built, it's cheap to operate. And there's no major climate effect, except there are spent fuel rods, the waste products you have to hide in coffins and hope there's no earthquake that puts them into the water supply. Nonetheless, there is a lot less pollution from nuclear reactors than fossil fuels. But again, they're not perfect. There are disadvantages. The spent fuel rods are radioactive and dangerous for decades. They have to be cooled and carefully stored. Another disadvantage is that uranium is ripe for theft. In the right hands, uranium fuel can be made into nuclear weapons, though that is exceedingly difficult to do. It usually takes a state actor to do that. But malfunctions can lead to explosions, radioactive contaminations, and when nuclear reactors go wrong, boy is it dramatic. 3 Mile Island, 1979. This is a nuclear power plant in Pennsylvania where radioactive coolant leaked into a building, causing the uranium core to suffer a partial meltdown. That is, things got real hot and started melting, but it was only partial. It was contained. This accident was caused by mechanical failure and inadequate personnel training. Modern nuclear reactors are much, much better. People are better trained now, and engineers are better at building them, in part thanks to the fact that we've had some failures like this. You learn from failure. Fortunately, the radiological contamination was limited to the facility. There weren't radioactive materials spewed out all over the region, as there have been in other nuclear disasters. But even a year later, the contaminated building was unsafe to walk in. It was still abandoned. It took 14 years to clean up this accident at a cost of billions of dollars. The cleanup cost was $1 billion. Property damage over $2 billion. And the result was, as it should be, increased regulation on nuclear power plants. You got to build them right now, and you got to train your people. But it also galvanized activism against nuclear power. It became harder and harder in the United States to get new nuclear reactors built after this, particularly after Chernobyl, 1986. This was in Ukraine. This was not a nuclear explosion. There's no nuclear bomb going off. It was a steam explosion. But that steam explosion released radioactive materials into the air, and resulting in a fire that lasted for 9 days. 2 people died from the initial explosion, 134 hospitalized, and 28 died from radiation, with an estimated 4,000 cancer cases. And by the time it's all said and done, that number might increase up to 40,000 or more. An entire city was evacuated, Pripyat, but even the evacuees didn't escape harm because the road leading out of the city, which they were all stuck in a traffic jam trying to escape, that road was already contaminated and radioactive. They were receiving radiation from the road as they were stuck in traffic. 350,000 people overall evacuated permanently. 100,000 square kilometers were contaminated with radioactive fallout. That means little radioactive bits floating in the air that fall to the ground. The Ukrainian capital, Kyiv, suffered radioactive contamination to its drinking water supply. It had to switch rivers and get its water from a different river. And Chernobyl accident was caused by a flawed reactor design. So the engineers of the world learned a lot from this mistake. More recently, Fukushima in 2011 in Japan had 3 meltdowns caused by an earthquake. And the Fukushima was much better designed than the others. The radioactive material was contained much better than the other 2 disasters. There were no immediate radiation deaths. We do expect hundreds of cancer deaths from this. They had to, and about 1,600 people died while being evacuated from nursing homes. Nevertheless, controversial opinion, nuclear power still, even fission power, with all of its dramatic failures, better than fossil fuels, because although these failures have been dramatic, their lasting damage to the planet and to human beings is nothing compared to climate change. But fossil fuels, nuclear power, they're not the only ways to get energy. We have lots of ways to get energy, some of which are renewable. These are sources that keep going. Wind, solar, that is getting energy from the sun. Geothermal, taking heat from hot spots in the ground. Hydroelectric, that is waterfalls. And tides and ocean waves can also be used to generate power. Wind is, boy, is it on the rise. Wind technology has gotten really cheap, and it's plentiful. Lots of places in the world have lots of wind, and that land can be double used to graze animals. So wind is cheap. It can be used most places, lots of places, not most places, and has a disadvantage that if you don't place the wind turbines in just the right place, they can interrupt bird migration routes and chop them in, kill them. We can also use the sun to get energy. There are 2 types of solar power. Passive solar just uses the sun to warm things up. So if you go camping, you can get a passive solar shower. This is just basically a bag with which you fill water, hang it in a tree, the sun heats it up, and then you pour it on yourself to bathe. That's passive solar heating, using the sun to heat things up. Some homes use passive solar heating as well. Active solar heating uses solar cells to convert sunlight into electricity. And solar cells have traditionally been very inefficient and very expensive. They're getting better, slowly. Sunlight is very plentiful in some parts of the world, particularly in equatorial regions and in deserts. Problem, of course, is the sun doesn't shine at night, and solar panels don't work very well when it's cloudy. There's another disadvantage that solar cells require some really hard to find minerals that have to be mined, and that has an environmental impact. So the energy problem can be basically broken down into 3 parts. Production, transmission, storage. Maybe we'll add consumption as a 4th part. Production, that's what we've been talking about. There's lots of options. We have the technology right now. We just need the political will to choose based on the good of everyone on Earth instead of the continued profit of the people who've already been profiting. We have the technology. We can do it. nuclear fission, maybe nuclear fusion in the future. There are people that are right now building nuclear fusion reactors, but they're a while from being online. We'll talk about that later. Renewable energy, wind, solar, fossil fuels, the old standby. The second problem for energy is transmission, and that's already solved pretty much. Power lines. Right? Power lines are really good. Power lines are really good at transmitting electricity from one point to the other with very little loss. A huge problem that has not come close to being solved is storage. Batteries. I don't know if you're aware of this, but batteries suck. Even the best batteries suck. This battery in my phone won't even keep the phone charged for like a day. Batteries suck. Even the best batteries are terrible. We got to figure it out. How to make better and better batteries, especially if we're going to use, for example, solar power. If you are completely dependent on solar power, you got to store that energy up for the nighttime. Same with wind. If you are completely dependent on wind power, then you've got to store that wind for the calm days. Right now, that's not what we do. Right now, we use solar and wind to supplement the electrical grid. And then when the sun's not shining, when the wind's not blowing, we use other sources. So right now, wind and solar make a good supplement to the energy grid. But if we're going to rely more and more heavily on them in the future, as hopefully we will, that means we're going to have to be able to store enough energy to power cities, batteries that can power cities for days and weeks. And we're not even close to that. In fact, the best battery in the world right now today is called the giant Tesla battery in South Australia. It collects energy from wind turbines and then stores them in this battery that you're looking at right here. This battery holds enough energy to power 30,000 homes, a small city, for 10 minutes. 10 minutes. Okay, that's something. That's a start. It's the best in the world. But if we are going to rely completely on renewable energy, on wind and solar, then we're going to need a lot better batteries than this. We've talked about the three energy problems, which are which are transmission, production, and storage. We might consider a fourth problem to be consumption. And that's something that we're just beginning to get a handle on. What you're looking at here is a graph of electricity generation, all the electricity that has been generated by power plants since 1950, per year since 1950. This is in billions of kilowatt hours per year, I believe, per year. I have to go back to the source on that. Don't quote me on that. Okay. But one thing to notice, from 1950 to 2000, electricity went up and up and up and up, and now at 2000, it's kind of leveled off. What happened? Well, since about 2000, our light bulbs and appliances have gotten more efficient. We have leveled off our energy consumption by using more efficient products, like these light bulbs that everyone hated at first because they shine a different color than the old Edison bulbs do. That's real. That's true. But they are also much, much more energy efficient, and they've contributed significantly to the leveling off of energy consumption. Also, modern appliances are more efficient. They use less electricity to do the same job. Homes now, on average, are better insulated, so it takes less energy to heat and cool them. All of this has resulted in a leveling off of energy consumption. Is there a golden ticket? Is there a golden arrow? One source of energy that could give us all the energy we could hope for? Maybe. Nuclear fusion turning small nuclei into large nuclei, releasing lots and lots of energy. That's how the sun shines. Can we replicate the conditions of the core of the sun on Earth? Yes, we can. That's a hydrogen bomb. Okay, can we do it in a way that doesn't destroy everything, but instead generates electricity that we can then harness? That's a little harder. So far, when we replicate the conditions of the core of the sun on Earth, we destroy things. That's a bomb. But can we do it in a way that we can just take electricity and use it? Well, possibly. We're not there yet. But if so, oh my God, problem solved. The fuel is abundant. We're talking hydrogen, which we can get from water. Practically no pollutants, very, very little pollutants. There is some radioactive waste, but it has a short half-life, so it goes away quickly. So it's not nearly as dangerous for the environment as a fission reactor is, or could be. And there's even more energy in fusion than there is in fission. So the dangers of a fusion reactor are greatly reduced compared to a fission reactor. Now there are problems. Most reactor designs right now require temperatures even hotter than the core of the sun. The sun's core is 15 million degrees. That's relatively cool compared to what we would have to make. And the reason the sun can get away with fusing hydrogen into helium at only 15 million degrees is that the sun's core is extremely dense. Our fusion reactors would not have fuel that is as dense as the core of the sun, which means we need that fuel to be even hotter to make up for the lack of density. Most fusion reactor designs right now require 100 million degrees, 100 million kelvins. It's about 100 million degrees Celsius. Another disadvantage, hey, no fusion plants are yet operational. They require massive initial investments. I mean, we're learning on the way here. You've got to develop the science and the engineering at the same time as creating the core of a star in a laboratory. But people are working on it. Several independent groups throughout the world right now are working on this problem. The one that seems likely to achieve it, or that at least they're on their way, is ITER, the International Thermonuclear Experimental Reactor in France. They claim that they're going to be ready, fully operational, by 2035. That's 15 years from now. They've already spent $14 billion, and it's just getting started. But if they're successful, we will move into a new phase of energy for humans. All right, well, we've survived that. So when I say physics, you say rocks. Physics! Did you say it? Yeah, you did. Repeat after me. While fossil fuels pollute the world, wind turbines cleanly whirl. Fusion accidents lead to cancer. Fission accidents lead to cancer. Hope you can read better than I can. So fusion might be the answer. When I say physics, you say rocks. Physics! Did you say it? Yeah, you did. Lecture quiz 16 is posted. Go do it now. Do it now while the material's fresh in your mind. Use your notes, because you took notes, didn't you? Yeah, you did.